Okay, guys, today inshallah we're going to continue what we started last time. Last time we started in section 2 of chapter 6. So we're still talking about the covalent compound. So we know that covalent compound is a covalent bond. It's kind of the bond in which two atoms are going to share electrons to complete their outermost energy level or to decrease the potential energy. And we said that two atoms are going to share in electrons of the outermost energy level, and they gonna keep going for closer to each other until they reach a certain distance, which gonna stabilize the force of repulsion between the similar charges of electrons and nuclei, and the attraction force between the positive nuclei of the two atoms and the electrons of the outermost energy level, which cause that each compound or each covalent compound have a certain bond length and certain bond energy. And we said the bond energy, the amount of energy needed to break the bond, and equals to the amount of energy which is released during formation of the bond. Today, inshallah, we're going to pass to another part, which is octet rule. What is octet rule? As we know that all noble gases, they are stable. Anyone could remind me why noble gases are stable, guys? Anyone have an idea why we said that noble gases are stable? No one?
Because their energy levels are filled.
Yeah, so we said that because their outermost energy level are filled. As we know that noble gases, they are located in group 18 in the periodic table. So that means they belong to the B block, which means that their outermost energy level, okay, that contain sub energy level S and P. So S and P actually are completely filled. S is completely by 2 electrons, while P is completely filled with 6 electrons. So like this, that's why we said that they have 8 electrons. That's why we said octet. Octet means oct means 8 in Latin. So octet rule, that mean atoms that have 8 electrons in outermost energy level. So that's why noble gas is considered to be stable or have low potential energy. So they could found in nature as a single atom. They don't need to react or forming compounds. But other elements, other substances, they try to be look like the nearest noble gas. They try to fill their outermost energy level. They seek for completing their S and B sub energy levels with 8 electrons like noble gases. So that's belong to all elements except of course hydrogen that or helium, because helium just filled up by 2 electrons as it has only one energy level. So it has only sub energy level S, so it could be filled by 2, but except hydrogen and helium, other elements, they try to fill their outermost energy level by 8 electrons. That means the S and P sub energy levels be completely filled with electrons. Let's take an example to clarify the idea for us. For example, here, look with me. If we have fluorine, for example, so fluorine is F9. So if we just said that here, F9, that's fluorine. Okay. So if we start to make the electron configuration, we're gonna find that 1s2, 2s2, 2b5. Okay, so in that case here we're gonna find that there already the outermost energy level is energy level 2. It has 2 sub energy level S and P, as is completely filled by 2, while B still lag for 1. So once we start to form the compound F2, okay, we're gonna find that the 2 electrons here, okay, so 1s2, 2s2, and 2b, okay, it has 5, 1, 2, 3. Then we start to, so it has one single electron in orbital of 3b, and the other atom of fluorine also will have the same idea. So the other atom of fluorine will be the same. 1s has 2 electrons in the orbital, 2s also 2 electrons, okay, and 2b has 5, okay. So like this, finally still have 1. So this one and this one, they could be shared together, and in that case if we counted, that will be 2, 4, and here 6, so 8, and the same in this one. So like this, they could form a covalent bond by sharing the electron which is single in the orbital of sub energy 2b. So here that's represent the idea of the forming covalent bond, or how they share to reach the octet rule. Okay, so the same also hydrogen. Okay, hydrogen just has 1 electron, so 1s with 1 electron, while chlorine, sorry guys, while chlorine Cl17, so Cl17, once we make it here, we find that 1s2, 2s2, then 2b6, 3s2, then 3b, we're gonna 5, it has 5. So simply the chlorine has 1 electron, okay, single in orbital of 3b, And here in hydrogen, it has one electron single and one s, so this they could share together. In this case, hydrogen will have two and one s, so it will be look like to the nearest noble gas, which is helium, while chlorine will have 8 in the outermost energy level. That means the 3s will be complete with 2 and 3p will be completed with 6. So like this, it reaches the octet rule and becomes stable. So that means almost the elements in the periodic table, they follow the octet rule, okay, to be stable like noble gases. But we still have some exceptions. There are some exceptions in that point. What are the exceptions? Exceptions, it means some elements or some elements in the periodic table during their reaction, okay, so they try to, okay, fill their outer energy, but they don't follow the octet rule, which means they will not just be stable by having 8 electrons in the outermost energy level. They may share with more electrons than the electrons of the outermost energy level. It means here they will not only use electron in S and P, they may involve of D also. Okay, let's take an example to clarify the idea. To clarify the idea here, that cases or these exceptions happens when elements they react with high elements of electronegativity. For example, once we have PF5, okay, phosphorus pentafluoride. So phosphorus pentafluoride, phosphorus, suppose its atomic number P15. So once we start to make the electron configuration, 1s2, 2s2, and 2b6, then okay, we have 3s2, and finally we have 3b, okay, that's gonna be 3b, they are gonna be 3, okay. So that's where what we have here in that case. Fluorine, actually, it's F9, so 1s2, 2s2, and 2b, okay, let's have 4, and so they are 4, we still have 5, 1, 2, 3, 4, 5, okay, so like that. So fluorine, suppose that it's gonna share by 1 electron, and phosphorus, suppose it's shared by 3. So the valence electrons of phosphorus represent 3, while the valence electrons of the fluorine resemble by 1. But in that case, we find that there are 5 fluorine atoms are bonded to 1 phosphorus. So what happens? Because fluorine has high electronegativity, in that case, the nucleus of fluorine is able to attract the 3 electrons which found in the sub-energy 3b, but also it's able to attract the 2 electrons which found in 3s. So in that case, we're going to have a covalent bond that involve, okay, 5 atoms of fluorine, each one shared by 1 electron, while the phosphorus will share with a 5 electron, the 3 electrons which are free in the sub-energy 3b, and also the 2 electrons which found in 3s. So here we have extra valence numbers. The regular one is 3. But in that case only, when it reacts with higher electronegativity elements like fluorine, oxygen, and chlorine, it could share by 5 electrons, which are the 3 in level P and also the 2 in level S. The same also in case of sulfur fluoride. Sulfur, suppose that it's S16. So as X16, so suppose that you're gonna have 4 electrons in 3b sub level, okay, so that means it could share by 4 electrons. But in case of fluorine, it also will attract the 4 electrons which is already found in 3p plus the 2 electrons which found in 3s. So in this case, it could share by 6 electrons, not just 4. So that there are exceptions of octet rule, okay, or that they are the elements, or that the cases which represent irregular way or abnormal way in the reaction, depends on the electronegativity of the element. So now we pass to another part here, which is something called the electron dot notation. So what is electron dot notation? So let's see here, guys. So we said here octet rule, as we sorry. So we said that okay, renewable gas are unreactive, as we said, because their level is completed. So S and P, they are completely filled by electrons. So other elements try to do that, and we call this the octet rule. Okay. Then we said that here, okay, there are some exceptions of octet rule, like hydrogen, because hydrogen just has 1 electron only, so you just need to share by 1 electron to be like a nearest noble gas, which is the helium. Okay, and the other elements, okay, that like boron, for example, they could be filled by 6 electrons. That will make it stable, okay, during chemical reaction, so it doesn't follow the octet rule. And also we find some elements or other elements, they even could expand the number of valence electron once they react with high electronegativity atoms like fluorine, oxygen, and chlorine. Then we pass to the electron dot notation. What is electron dot notation? Actually, the electron dot notation, it's a kind of electron configuration which represent the electrons in the outermost, or the valence electrons in the outermost sub-energy level. So let's take an example to represent the idea. For example, when we say Na, okay, so here, when we say nitrogen 7 and 7. So once we start to make it here, we know that the electron configuration of N7, 1s2, 2s2, then 2b3. So in that case, okay, we are gonna just represent the unfilled, okay, outermost sub-energy level. So we are gonna say nitrogen, and we make, okay, just like 3 dots that represent the 3 electrons in the outermost energy sub level. Okay, so the completely filled is not represented. Okay, so here we don't represent the 2 electrons in the S because it's already completely filled, but here B only represented because it's not completely filled. Let's take another example to clarify the idea. For example, we have oxygen, so O8, so 1s2, 2s2, and then, okay, 2b, then gonna be 4. Okay, so in this case we're gonna draw oxygen like this. Okay, 1, 2, 3, 4. Okay, so here like this. Okay, it's represented by the number of electrons that's found in the outermost energy level. Actually, the valence electron here, they are represented by 6, so we just folded that's here. So the completely filled sub-energy levels is not, or the completely filled sub-energy levels could be represented. That means we are going to put like this. So in that case, they will be showing the 6 electrons, representing the entire electrons found in the S. And here also they are 5. So I could make it like that. Okay. So here, like this case, represented by 5. So should we represent even S and here represent S? Yes, we could represent them because that represent the outermost energy level. We represent S, but we don't represent the 1s here or 1s here because it's already another main energy level. So we represent the entire electrons which found in the main energy level. So in the main energy level 2, we have 2 electrons in S and 3 electrons in B. So that means the total dots which are going to represent are 5. Why? But because why, if the only electrons which will be involved in the reaction are the electrons in the sub-energy B? That's a normal situation. But for example, if nitrogen is reacted with a higher electronegativity element, it may also share with these 2 electrons. So in that case, its valence electrons could extend or expand to 5, not 3 only. So that's why we should represent the number of electrons which is already found in the main sub-energy level, not the main energy level, not sub-energy levels. So here, let's see. That's it here, guys. So we need write the electron dot notation. Let's try to answer this together. Okay, notation for the hydrogen. So if we just need hydrogen, it's just H1. So as it H1, okay, and here says for nitrogen, and also he asked to. Let's try to find that, or how we answer this. So hydrogen H1. Sorry, why the pen is not working? So hydrogen H1, so 1s1, so like this hydrogen, we just make 1 dot. Nitrogen N7, so 1s2, 2s2, 2b3. So what are the outermost energy mean level? That's 2. How many electrons includes 5, so we're going to represent by 5, so n, and we are going to make it 1, 2, 3, 4. Then we start to look at A1, so it's become like 5 like this. Okay, so here like that, that's the idea, and that's here the meaning of the electron dot notation, or how the electron dot notation is represented. I hope that everything is clear. And do you have any question, guys? Here, anything is not clear? Guys, everything is clear here? Is it clear, Gizi? You say no or yes?
Yes.
What?
Clear.
Clear?
Yeah.
Okay. So guys, please, we already studied the page 182 to page 184. Please study this part very well from your textbook. And if you have any question, you are welcome to ask anytime. Okay, so anyone have any question right now, guys?
شكرا.
Okay, guys. Thank you.